All right. Hello, everybody. So it's my privilege to be talking to you about the optical and near-infrared view of planet-forming disks and protoplanets. Chapter number 17 has been written by Miriam Benisty, our leader, by Carsten, Dominik, by Follette, by Antonio Garufi, that's me. I'm from the Osservatorio Astrofisico di Aceto in Italy, by Ginski, by Hashimoto, Miriam, Keppler, and Monnier, and more importantly, by Kley. Kley is our colleague that unfortunately and prematurely passed away in December 2021. He's very much missed by his colleague for his optimism and kindness, and on a more personal level, I really remember the first time I met him. It was 10 years ago. I was in Germany for my first international conference talk. I was really nervous, even more nervous than I am now. And they were just giving me the right words. He was just trying to calm me, so I could really appreciate his humanity since from the very beginning. We have an obituary dedicated to him and written by Richard Nelson at the end of the chapter. Okay, let's start with the outline. So this is the outline of the chapter and of the talk. As you can probably see, we have two main topics. The first is planet-forming disks, and the second is protoplanets. As a community, we have much, much more on planet-forming disks, of course, but the fact itself that we are here talking about a protoplanet being detected and characterized is already a revolution by itself. So in this regard, we could even dare to say that protostars and planets should be protostars and planets and protoplanets now, finally. So let's start with the motivation that led us to write the chapter. These are questions probably in common to most of the talks of today and of yesterday, even tomorrow. Where and when and how planets form in the disk? How is the diversity that we observe in planetary systems somehow inherited from the planet-forming disks? And how does the planet or the forming planets in the disk affect the disk structure? And to actually address this question, we have a number of goals. No, sometimes it doesn't work. Now it works. The first is to find protoplanets. The second is to determine the disk demography in a similar way to what has been done by our colleagues working with planets. And the third is to characterize substructure in the disk and any sign of gas-dust differentiation, because these are the two main imprints of the interaction with the planets. And here you see a number of figures, that are teaser of what I will be talking about. So all these questions were somehow tackled much better in this last decade, thanks to ALMA, yes, but also in parallel thanks to high contrast imaging in the visible and in the near infrared. And this is the chapter that we wrote. And so in particular, this is thanks to the extreme adaptive optics techniques and system that we have now, and I will tell you in a few slides. And as I told you, even only the first detection of a protoplanet has revolutionized the field. This is a collection of disks that basically represent the pinnacle of our capabilities to actually detect and characterize planet-forming disks in the near infrared. So some words about the methodology. Try to keep it simple for everybody. Here we have, if we work in the near infrared, we have three main problems. The first, that of course, disks and planets are small or on short separation from the star. So we just need to use the biggest telescope that we have on Earth. At the moment, it's 8-meter telescope. It's going to be better soon. The second is the effect of the atmosphere. If we work from the ground, we need to use adaptive optics in order to correct for the aberration introduced by the atmosphere on our stellar flux. So this is what we are without the adaptive optics, and this is after correcting for this aberration. And in particular, in the last decade, great progress has been done in this regard with the extreme adaptive optics. And you can probably guess that even after correcting for this aberration, we are left with the PSF from the stars, basically the response of the stellar light through the telescope. We can still see that we have disks and planets somewhere behind the PSF. So this is the third problem that we have. If we work in the near infrared, the star is the primary source of photons. We have to somehow cancel this dominating stellar flux. And to do it, we can use a coronagraph, yes, to mask the inner part of our PSF, but we also need to develop some differential imaging techniques that are basically helping us to disentangle different types of emission. And I will tell you a few words on the 3 most important differential imaging techniques that have been used in this decade. The first is the easiest to be understood, but it's probably the most technically challenging somehow, and it's simply the reference star differential imaging. So the concept is that if we have a star that is very similar in flux and in temperature to our target star, we can observe both and then subtract one from the other, and in principle be left with anything that is not PSF, so the disk and the planet. Okay? Easy said, not so easy done. The second is the PDI, polarization differential imaging. And this exploits the fact that the stellar light is mainly unpolarized, whereas the scattered light from the disk is to very large extent polarized. So if we can just use a polarimeter at the telescope, we can basically get rid of anything that is not polarized and be left with the scattered light, since the scattered light from the disk is polarized. That's for any kind of scattered light from in nature. The problem is that the thermal emission from any planet embedded in our observation would not be observed because it's also not polarized, not at least to a large extent. So this is good for characterizing disk, but not for planets. For planets, much better to use the angular differential imaging, and this is a technique that actually exploits the rotation of the Earth. The rotation of the Earth is basically because the Earth rotates, the sky rotates, and so throughout our observation from 2 a.m. to 4 a.m., basically the sky will rotate, and therefore any real object in the field, if we tell the telescope not to correct for it, will rotate in the field of view. So basically my thumb, with respect to the center of my hand, is basically moving in the field of view. By doing so, we can basically construct an average of our observation, and the PSF would be the same, because the PSF does not change throughout the exposure, because the PSF is basically the response of a telescope to the stellar incoming beam. And so after we have done this average, basically we just have to subtract any single frame that we have and be left with anything that is not the PSF. So basically, in this case, the planet. Then it's just an easy game. We just have to derotate all the single frame that we have, stack them together, and in principle, we are left with the image of the planet. But going back to the scattered light from the disk, this is a sketch to show you what we are actually observing when we do it. And you have to consider a photon that is released by the star and then is scattered at different angle by the disk. So small angle, 90 degrees, and a large angle toward the observer. Okay? On top of this, not all the photons will be polarized. So the fraction of scattered photons that are actually polarized depends in turn on the scattering angle. It will be maximized in this direction here, 90 degrees. So what do? We construct what we call the scattering phase function. So basically the number of photons scattered per incident angle. Okay? Let's do it together. On small angle, we'll have a lot of scattered light in principle. So the I continuous curve that you see here, intensity. On 90 degrees, actually this is decreasing, significantly decreasing. And now if you observe the dashed line here, this is the fraction of scattered photons that are polarized. And this is maximized at 90 degrees. So the two things go somehow in the opposite direction, all right? And for small angles, actually, the situation is that both decrease. So somehow the final scattering phase function that we have is that P over I and the intensity. What we observe is the convolution of the two. It's the P, basically. So this is the number of polarized photons that we receive, and would be a curve like this. This would be very important in a few slides, because with this, we can characterize the dust grains in the disk. Okay, this is where we stood in Protostar and Planet 6. At that time, we mostly have those observations from the near-infrared from HST, but also with some pioneering work from the ground, as you can see the first two and the last two. But most of the observations were actually from HST. Now the situation has completely changed. Most of the nice images of disk in the near-infrared that you have seen come actually from the ground, in particular from Subaru High-Chow, from Gemini Planet Imager, and from the Altisphere. There are the 3 telescopes that are equipped with the polarimeter and the adaptive optics. And this is again figure 1, but you can see clearly the improvement that we have achieved in the quality of the images. This is another example that we wanted to put within VLT facilities, VLT NACO versus VLT sphere, same object, same spatial scale, same wavelength, where you can clearly see the quality significantly improved. It's not only a matter of quality, though, it's also a matter of quantity, especially because of large survey that we could carry out with these telescopes. The number of individual disks being observed has dramatically increased, in particular after Protostar and Planet 6. Not only that, but also the coverage in the stellar parameters that we have now is much, much better. In the beginning, the blue points here were mostly Urbic stars, very bright Urbic stars. So within the framework of isochrones, relatively old and massive stars. Now we are populating this region here of low mass young stars, T-Tauri stars, basically. You can see two deserts here. This one is real, it's a probable absence of disk around this type of star. And this is actually technical. These stars get too faint for our adaptive optics telescope to actually work. And so this is the limit that we have to overcome before Protostar and Planet 8. So let's see some of the results that we have obtained, in particular about the protoplanet, the planet-forming disk. The big advance that now that we have achieved is that we can finally constrain what we call the intermediate size disks. So from this comparison here, you can see that from HST, we could basically probe the outer part of a very large disk, whereas with ground-based observation, we actually probe the most interesting region of a disk, which is where planets are supposed to form, from 10 to, let's say, 100 AU. So in this regard, the two telescopes were kind of complementary because we are not really sensitive to this outer region here. But we must consider that only few of the disks are as large as this. So in this sense, we have access to many, many more disks the HST could not observe because HST could only observe the exceptionally large disk. Finally, in the future, hopefully, we will also characterize a small disk, which is also a very important fraction of disk in the forming region. As we also heard already from yesterday's talk and today, we probe some different layers, some different components with respect to ALMA. In particular, we probe the small dust grains at the disk surface. And you can see here another comparison, we already saw some, between the ground-based near-infrared facility and ALMA. You can clearly see the flaring structure that we probe, this dark lane here coming from basically the midplane and the backside of the disk here. You can clearly see the different vertical structure that we probe with respect to ALMA. And from this figure here, you can also see the different radial extent that we probe. Clearly, we go much farther out because the small dust grains are very well coupled to the gas, and so we really go where the ALMA continuum probe in the large dust grain cannot go. And the comparison is very important. I will stress during the talk that actually the comparison between near-infrared images and ALMA is very important to characterize a number of dust processes, including vertical setting and radial drift. One of the things that we have understood that the brightness, what we observe actually from this image, is primarily determined by the illumination pattern. So the stellar luminosity, the presence of shadows, and the flaring surface. We have a secondary effect on the dust albedo, but we know now that the primary reason why a disk is faint or bright depends on how many photons can actually reach the outer surface, okay? In some situations, many of the photons will be actually intercepted by the inner disk, reprocessed in the near-infrared that we can observe from the spectral energy distribution, whereas some other could be free to actually illuminate the outer disk and be scattered, okay? And in general, I think we have a dichotomy. Actually, we have a continuous distribution, but let's say we have a dichotomy between bright disks are those with a large cavity, where a photon is free to actually illuminate the outer disk, and the faint disks, where basically no cavity exists. So people in the field actually know that we are talking about transition disk or every group 1 in the old MEUS classification versus full disk with no large cavity, also known as group 2. Back to the characterization of dust grains from the disk surface, what we can do is actually to constrain it through the scattering phase function. Remember how many photons we have per incident angle. So what we can do is a simulation of what is this, depending on the different grains that we have at the surface. It's the work by Ryota, where you can see different monomers making up the aggregates that are scattering the photons. So you can see different curves, blue with blue, orange with orange, green with green, and so on. you can see the very different scattering phase function expected from different dust grains, okay? And now we can put the observation on top of it, a real observation. We can constrain now, thanks to our knowledge of this geometry, we can constrain this. And so we can start to rediscriminate among different types of disks somehow, with different grains. And in this example here, we can probably see that some disks are monotonously increasing towards small angles, and some other actually tend to bend to small angles. So this would be actually representing two classes of objects, some with large aggregates, like this, and some others with more compact objects, like this one here, with fewer monomers. So this is very important to characterize these dust grains, because we know that in the end, these dust grains will grow larger and larger, will be detached from the gas dynamic, will be settling toward the midplane, and they will be trying to get more and more compact. So observations actually show that aggregates are more on the surface, whereas in the midplane we have more compact grains. So it's probably probable that actually the grain growth proceeds in this way, with more aggregate structure and then compact toward the midplane. Let's move to the substructure topic, which is very appealing to most of us, I believe. And we have one headline, I think, over this last decade, that is that practically all bright and extended disks show subtractions. In the chapter, we don't really care about the origin of this subtraction. We mostly care about the demography of substructure across different properties. And we have a sort of visual synopsis of all the different substructures that we have. We saw this already yesterday from the talk by Shawan and Andrea. We have the spirals. We have this dark shadow lane that can be more or less broad. We have rings, we have possibly concealed planets. If they are concealed, we don't see them actually. We have a large cavity in some cases where a planet could be detectable, and you already know what object is this. And in some situations, we have a global shadow where basically we cannot really observe the disk in the near infrared just because it's completely shadowed by its inner region. Let's start with spirals. Spirals themselves show a variety of morphology if we observe them in the near infrared. And as said yesterday, there's just one case where we know where's the origin. It's actually when we have an outer companion. But if we don't have this outer companion detected, actually we don't really know what is the origin of these spirals at the moment. In some cases, I believe it's environment, because you can really see these spirals replicating very similar to very, very large angles. So somehow it really seems that the interaction with the environment is responsible for it, probably because this is accreting, material accreting onto the disk. In some other cases, we don't really know. It could be instability, it could be the presence of embedded companions, planets, or substellar objects. It can be something related to the inner disk somehow, but in general, we don't have an answer to that. And you can see also two different type of spirals. Also, we saw yesterday, the spirals are not really there in ALMA. When we have spirals in the near infrared, we actually have a structure like this in ALMA. So two concentric rings with the outer one, in this case, showing an azimuthal asymmetry. So another example of why it's important to actually combine ALMA observation with our near infrared images. And I want to stress it's important also to keep in mind that for spirals, is this trend here. Here I'm just guiding your eyes with this bubble. If you put basically the spiral disks in a distribution of near infrared excess from the spectral energy distribution, you can clearly see a distinction between the disk with rings and the disk with spirals. So spirals go with the very hot inner disk, where basically most of the light is reprocessed by the disk. I don't have an answer to that. I don't think that anybody has it, but it's something that we must keep in mind. Somehow the outer disk knows about the inner disk. Also, it's not really due to gravitational instability, I believe, because the mass is clearly not the parameter shaping these spirals. Similarly to spirals are shadows. So similarly to spirals are diverse, the shadow. In particular, we divide the shadow into narrow shadow, like in this case here, and broad shadow. They can be even larger than 180 degrees. And we know now that these are due to, we believe now that these are due to actually a misaligned inner portion of the disk that can cast a shadow on the selective part of the disk. This can be warps, can be broken disks that are actually misaligned. And we also have a temporal variation we can see on a day and week basis. And this is a sketch to actually show this anti-correlation that I mentioned already. Now, when we have basically a bright inner, much near-infrared excess, the disk is faint, whereas when the near-infrared excess is low, then the disk is very bright. But those disks with azimuthal shadow, they are actually exception. They have an even higher near-infrared excess, as for spirals, if you remember. So it really seems that there is something in the object with a high near-infrared excess is perturbing the whole disk and creating shadows, spirals, and azimuthal concentration of material probed by ALMA. This is another beautiful example where you can see some probably accreting material is perturbing the disk dynamic and possibly be responsible for any sort of misalignment that can be seen with the interferometer in this case and be casting a nice shadow that you can appreciate. Okay, let's move to the second part of the talk, which is protoplanets. And as I mentioned, this is a big revolution that we have had in our field. And of course, we must start from PDS-70. I believe that everybody in the room has seen this image. PDS-70b is sitting here, the first robust detection of a protoplanet embedded in a disk. And you can clearly appreciate that we have detected this just because it's completely detached spatially from the disk, right? It sits well within the cavity. This was initially found with ADI, angular differential images, the technique that I told you about with VLT sphere, but also with NACO, Gemini, and EASY by Miriam, Keppler, and Müller. And then was confirmed later on, first with H alpha, was detected by Kevin Wagner and Sebastian Hufford. You can see here detection of H alpha, so somehow we have some sort of accretion probably onto the protoplanet. But then it was also raised PDS-70c that you see here. And actually, this was somehow supporting that this kind of protuberance that was seen in the original image was not actually the disk, but it was actually another protoplanet. So again, you can see that the effect of the disk is disturbing for us. The disk contamination, to actually be able to understand whether a protoplanet is real or not, is important. Another comparison with ALMA, another parallelism with ALMA is here, probably the strongest one that we have in the paper by Andrea Zell and Miriam Benisty. You can see with different angular resolution, PDS-70c, the circumplanetary disk of the PDS-70c was found by Andrea. Actually, the mass is very, very low compared to the mass of the planet, aiming probably at the late stage of accretion. And there was probably something not really associated to PDS-70b, some sort of emission close by. And with higher resolution, this PDS-70c was confirmed. And some diffuse, I believe, emission is actually detected here. It's not really associated with circumplanetary disk. It's most likely some sort of material which is connecting this protoplanet with the star. Okay, so again, this is a showcase of the synergetic employment of high contrast imaging and ALMA. We have a number of other candidates. The problem is always the same. All the time that a protoplanet is proposed, we realize that actually there is some sort of disk emission that is contaminating and can be actually misinterpreted as emission from the protoplanet. There's a number of cases. We have the detection of a B Auriga B, which is probably discussed tomorrow by Piller, and it's in the paper by Curry. And here we have two other examples. By Sasha Kwan, this is by Steph Salum. In all these cases, we have a strong contamination from the disk. So I think these are open, at the very least, they are open cases. In general, we were discussing with the co-authors, we thought as a community, we don't really have a unique criterion to disambiguate a protoplanetary detection candidate from a protoplanet that is confirmed. Here we're just listing three possibilities. So the detection of orbital motion, a spatial separation from the disk, which is of course ideal, like PDS-70b, but in the end we want to detect embedded planets, so we cannot always have this one, I guess. Or these are no, and accretion signatures. So we probably as a community at some point should be able to define a unique criterion to be able to raise a detection of a protoplanet. In general, I think that besides PDS-70, we don't really have a confirmed protoplanet, so the paucity of protoplanets is the main conundrum of the field. We have a number of these substructures seen. We believe that at least a part of this substructure are due to planets, right? if this is true, we would expect to see at least some other protoplanets. This is really the time to have planets. Planets should be in this protoplanetary disk. So the fact that we haven't seen is somehow a deficit from outside that we need to correct for, that we need to understand at least. So in general, the exercise that has been done by some author is to predict what is the mass of these protoplanets, provided that at least some of these substructures are due to the planets. So for example, here you have on the x-axis the mass of the predicted perturber that would be responsible for the feature that is seen in a number of objects. You can compare this with our current capability to detect these disks. So the horizontal color bar is actually our contrast curve, so basically our limit to the mass of the planet that we could detect. So it's clear in some cases, okay, we may not have seen these protoplanets just because they are lower mass, but in some cases we should have detected probably this lower mass. However, there's a big problem, I believe, is that the extinction exerted by the disk onto the planetary system is not really understood yet. So in general, moving to longer wavelength may help, at the very least L and M bands, so 4 and 5 micron from the ground. But in general, I don't think we have a good understanding on quantitatively of what is actually this effect. So in general, correcting this for the actual extinction of the disk will really help us to maybe understand that we are not there yet to actually be able to see these protoplanets. And so this leads us to the future prospect, what direction should we take now toward Protostar and Planet 8. And here we are listing 4 main directions, which is longer time, deeper surveys, radar wavelengths, and larger telescopes. The first is basically even only exploiting the data sets that we have now and and the data reduction that we have now and the telescope that we have now, we can still exploit another axis, which is the time domain. And this will be very important in the next few years to actually being able to characterize the variability of shadow, which is, as I mentioned, due to the dynamic of the inner disk, so the possibility that some unseen perturber is sitting very close to the star, the orbits of any companion or any possible protoplanet candidate, and the spiral motion, because this could also be related to the dynamic of an unseen protoplanet. Deeper surveys, we keep the telescope that we have now and we aim at the completeness of the sample. So we try within a certain threshold in distance, for example, a star-forming region, we try to actually be complete within the technical limit that we have now. So this is an example of that we are trying to put together with the Destiny/program with Christian Ginski as a PI, where we're actually trying to have a full demographic view of the Taurus star-forming region. We have, I believe, 45 disks ever observed by sphere in the Taurus star-forming region. The third is to go to radar wavelengths. This has, say, multiple application. L and M band, as I mentioned, are more suited to search for protoplanets. I am personally not sure yet about James Webb, but it's certainly good to try. The employment of near-infrared wavefront sensor is also very helpful. So in general, our adaptive optics use bluer light, and therefore we are very limited in some sort, depending on the brightness of the star. If we go to near-infrared wavefront sensor, actually you can see this example here from the Sphere Plus proposed white book. You can clearly see with the near-infrared wavefront sensor, we can actually switch from the 50% of the total number of young objects from this region here to nearly 80%. So clearly we can extend our sample to fainter sources, more embedded sources, because going to the red means going also toward more embedded sources. So this is a very interesting direction, I think, to take. And the fourth is pretty obvious, going to larger telescope. We are all looking forward as part of the near-infrared community to 30-meter telescope under construction on Earth that will revolutionize our sensitivity and an inner working angle that will allow us to actually detect very small disks, so actually the bulk of the planet-forming disk that we have, and possibly even close-in planets like PDS-17, but on a much, much smaller scale, like 5 or 10 AU. So, in summary, if we had to summarize 10 years, a decade of results in 4 very short questions, this is what we have. We have had a revolution in near-infrared imaging thanks to the extreme adaptive optics. I think this is no less than ALMA. Thanks to this, we have been able to characterize unexceptional disks, not the 5% of exceptional disks characterized by HST, but we really went to the 50%, to the average of, nearly to the average of disks. And the main result is that we have an ubiquity of this substructure. When a disk is bright and extended enough, then we have disk substructures. However, we could not yet connect this substructure to protoplanets. The discovery of the first protoplanets was evolutionary, but that's not enough to actually connect, of course, the disk substructure to the protoplanets. So our wish list, for with which I conclude the talk for Protostar and Planets 8, is on the one hand to actually characterize very small disks with 30-meter telescope that will allow us to have a complete view of planet-forming disks, to even have the equivalent of our planet-forming solar system nebula. The ubiquity of protoplanets is a bit provocative, at least to have more, for sure, more protoplanets than the few that we have at the moment. And then finally, to have a connection of these protoplanets embedded in the disk with the substructure that we observe, because this will give us the ultimate way, at least in the demographic sense, to be able to understand the planet formation, how it proceeds in planet-forming disks. With this, I conclude. I thank you very much.
Thank you very much, Antonio. So please line up. And again, junior people, please don't be afraid. Ask questions. Yes, Ilse.
Hey, Antonio. Thank you for the lovely talk. Oh, Ilse Cleaves, University of Virginia. I'm curious about the depth of the spiral features you're seeing in scattered light. You know, since we're seeing some disks that have very different millimeter dust structure, are we looking at a skin depth? How deep do these scattered light spirals, for example, or some of the features we're seeing that don't match the midplane, how far do they go down?
Specifically for spirals, we can assume that it's the same of the scattered light. So in the scattered light that we probe, the tau equal 1 surface is somewhere between the 12 CO and the 13 CO. I believe this is useful information for you. So typically we can constrain it's around, so let's say at 100 AU, we are around 18 AU in vertical extent.
Okay.
This is a typical vertical height of the disk that we probe in scattered light, but only for the brightest disks. So what we don't know is whether the faint disks are actually faint just because they are shadow, or they are actually flatter. This we don't know. We have no idea. But let's assume that a spiral is maybe a little bit more than an average disk. I would assume, yes, to have around 20 AU at 100 AU.
Interesting, thanks.
Let's go in the middle there.
Inga Kamp, University of Groningen. I was wondering, since we heard in the previous talk about all these winds that can entrain like 0.1 to 10 micron size grains, and that would act over, you know, maybe up to tens of astronomical units. So I'm wondering, what are your thoughts? Is it surprising that we don't see a signature of these kind of dusty winds leaving the disk with these adaptive optic systems, or are we just not able to see them, or should I worry about it?
I have in mind a paper by Barbara Colano's group where they simulate what is the polarized light that we should detect from this wind, depending on the dust grain that we have. And I believe they say that it's not surprising not to detect it. So in principle, it's okay that we haven't seen any. I think Barbara itself, she's trying to actually conclude whether some of our observation we see something. I'm not entirely convinced about that, but if we observe nearly edge on disk, in some cases we see some emission, let's say, and I think in the near future we'll have to understand whether this is actually due to any kind of disk.
Okay, let's go over there.
Thanks. This is Lina Kimmich from Heidelberg University. I wanted to ask you, could you tell me more about why shadow disks have a larger infrared excess in the SED?
So what is the reason?
Yes.
Okay. Hey, very good question. there must be some sort of perturbation that acts in two directions, in a sense. So if you draw something like this, the shadow itself is due to a misalignment. We believe that it must be, that there are radiative transfer simulations that show that actually even only a few degrees misalignment is enough to actually cast a shadow. And actually small angles are yielding a very broad shadow, while a larger angle of misalignment yield actually more narrow shadow. But on top of this, we need some sort of, I believe, of uplifted material, because in order to have more near-infrared access, we somehow have to more light that is processed. So whatever is responsible for this shadow, from my point of view as an observer, needs to both uplift the material and misalign. I guess it's not super hard, and it's a question for theorists, but we need to have both in this regard. So some sort of perturbation, and then the discussion has, I was just having with Andrea, is that whatever is responsible for that then somehow must be extended to the presence of spirals and of azimuthal asymmetry, because somehow the object that shows this shadow, and therefore a very high near-infrared access, also shows spirals and azimuthal asymmetry. So somehow I think we are really going towards some disk having a global perturbation that go beyond the normal ring disk that we have, where we see no shadow, no spiral, and no high near-infrared access.
Thanks.
Okay, let's go over here.
Jochen Stadler from the Nice Observatory. Thank you very much for this lovely talk, Antonio. I wondered exactly from this plot you showed. So we have some infrared observations where we don't see and detect the disk very far out. I was wondering if there's any comparison in the disk emission heights that we see, if we compare this to infrared observations, if they are quite high and puffed up, and that's also kind of an explanation.
You mean the inner disk then?
Yes.
The height of the inner disk?
Yes, yeah.
I'm not sure about the height. There is a paper, I think, by Alex Bond, using interferometric observation, where they found that actually the misalignment, so the degree of misalignment is consistent with the apparent shadow. It's not always true, but in some cases you can really see that the constrained misalignment between inner and outer disk is consistent with the shape of the shadow. But I'm not sure about the height. I'm not sure how much you can actually model the interferometric observation to actually obtain information about the height. In general, may I say the near-infrared access as a recipe as an ingredient of a recipe is somehow ignored by the.
So yeah, I was like connecting like 12 CO and 13 CO disk emission heights. So if you have like very flared disks that have very high disk emission heights, if they, on the other hand side, in infrared observations, then are quite shadowed or like not detected in the outer parts, because you have shadows that are cast onto the outer parts of the disk, and that's why.
Okay, so you mean like global shadows?
Yes,
somehow.
yes, global shadows.
For what I could see, typically the 12 CO goes, the height of the 12 CO goes with the brightness of the scattered light. So somehow it makes sense that the more extent is the disk in the gas, and the more extent is also in the flaring. In general, we don't have much observation about the faint disk. The famous disks that we always observe are very well studied, but the faint disk we don't know much in general. So I don't think there is a very interesting case, which is a HK loop, where we have a prominent detection of a disk with ALMA, but the disk is simply not seen in the near infrared. So that's a perfect case of a shadow disk. I'll be very curious to see a high-resolution image of the gas in that object, but I don't think we have any.
Thanks.
Okay, is another, I think? Sure.
Nader Hagigi for PSI and IFA Hawaii. Could you kindly go to slide 48, please?
48.
Yeah. What worries me about what you're showing is a huge degeneracy in producing this figure. The parameter space is infinitely large, and I'm sure you can reproduce any type of spiral arm or structure you want with different combinations. So would you care to comment on the degeneracy and the reliability of this figure, as a matter of fact?
I can't really comment on the simulation itself. I'm not really expert on this. I tend to agree. I tend to agree that we have to take this with much caution. In general, we just have to acknowledge the fact that protoplanets may be there. We don't know what mass they have, And as an observer, I'll keep searching, but as long as I don't have a mass of an observed planet and I can compare actually with the structure myself, I cannot say much. I agree that, of course, what we have in this figure here can be arbitrary. Not arbitrary, at least, but I'm sure you can change somehow the simulation. You know better than me in order to get very different masses.
Thanks so much.
Okay, let's go right here.
Hi, El Bogat, University of Maryland and NASA Goddard Space Flight Center. You had a plot that showed that fluffy aggregate particles end up on the surface of the disks and then more compact particles end up on the midplane. And I was wondering if the fluffiness of a particular particle lends you any insight into its composition and if how that affects what materials you might expect to end up on planets versus not.
Good question. I'm not sure we have gotten there yet. What I could do to try to see whether if we have these two sort of families, whether this somehow has any correlation with what we know of this disk here. For example, these two objects here would be the only one in this sample. Actually, 3 probably. There's also PS70, although we have some probably increase here. So the truth is, I don't know. I don't know how to reconcile this with the possibility whether there is any age spread. These are not necessarily younger than this, so we cannot really see any evolution from this object here to this. I believe this is what should be happening. So we start from this kind of range and then we go toward this direction. But at the moment, with such few disks, I couldn't say much. It's something, a direction we need to take for sure.
Thanks.
Maybe JWST maybe will be able to help. Okay, I'm trying to remember who was who, but I think let's go to the middle.
Nick Andriolo, Space Telescope Science Institute. I was wondering, what are the prospects for expanding these sorts of observations of like 100 milliarc-second disks around massive protostars and seeing these structures?
The problem is the brightness of the star. So when you go to more embedded sources, their brightness in the visible is dropping, of course, because of extinction. So far we haven't observed any protostar still embedded in the disk. Because we work on ground-based, we need adaptive optics. In the future, I believe that going to wavefront sensor can work at radar wavelengths. Then we could try to observe some of the protostars that are still more embedded. I have no idea whether this will work. It depends. Some probably not really embedded sources will still not be accessible, but at least we can probably switch our sample of class 2 disk at least to some class 1-ish disk or something like that. Thanks.
Okay, I think we have 5 people left. I think we can fit them in, so let's go over here.
So JJ Zanesi, UC Berkeley. So I'm very interested in these shadows. So I was wondering if you could comment on the time variability of them and what this points to for their origin.
So what exactly do you want to know? About the future direction to take, or?
Yeah, just how they're generated in the first place, what tilts everything.
Okay. Yeah, well, I mean, the problem is to really trying to have a map, a temporal map of this map here, like in this example here. Not sure it's moving, it's not moving now. But you can clearly see that on a weekly basis, this shadow moves somehow. So we can try to monitor somehow this and try to connect to maybe any variability that we have from the star itself. So we can probably trying to have some spectrum, some sort of monitoring on different direction. That would be the direction to take in order to understand what is actually responsible for this. Ideally, since we know that this shadow goes somehow with near infrared access, I would like to have a simultaneous monitoring of the shadow and on the photometry, at the very least a JHK photometry, in order to be able to see whether it's really near infrared access is changing along with the shadow.
Okay, let's go down over here.
Simon Portuguese, Leiden Observatory, Europe. I was wondering if it's possible to find any of the problems. You sort of open a can of worms, right, of observing disks, and many of the problems you describe would not really be present if you have circumplanetary disks. They cast shadows, but they also may be a mirror which is time dependent, depending on the precession of the disk and the orbit of the planet. Can you say something on the observation of these objects?
It's intriguing. So we need to find this circumplanetary disk. That would be a direction to take. So if you go back to this detection here, somehow I believe, I'm not really expert of millimeter observation, but I believe that in the community we have a similar problem, right? So in this case here, PDS-70C, yes, it's very close to the disk, but it's also somehow detached. So you can clearly see here that it's detached from the disk. I think, but there are people more expert than me in the room for sure, that the same problem of the contamination of the disk also applies to their observation. Maybe there's a different optical index somehow, but I believe in general the problems to find circumplanetary disk would also apply to millimeter observation. Whether this could be actually explaining some of the features that we see, I would be very curious. So you think a circumplanetary disk may even cast a shadow on the outer part?
Well, it may be inclined with respect to the rest of the disk, so it may be like a mirror of not having all the shadowing problems.
It's an interesting scenario. I don't know if this is possible, but it's an interesting scenario we should explore in the future.
Okay, let's come over here.
Hi, Antonio. Thanks a lot. Very nice talk. I'm Claudia Toci, is a Garshin. So I have a curiosity about your future perspectives. So do you think we have to wait PP8 before having some data on faint or compact disks? Or do you think we can try to do something with the current capabilities, at least on some not that faint, not that compact source?
Faint and compact. So the direction of compact can be explored now. What we can do is to detect compact disks in polarized light, in scattered light. So we can actually have a detection of polarization within the inner beam, so below the resolution that we have. And in principle, we can model this polarized emission. But we can just say whether the disk is there, how much is inclined, of course, model dependent, and no more than that, I would say. It's already something, so it's already something that we can really constrain this, because we had a problem of the instrumental polarization so far that has been corrected thanks to a fantastic pipeline by Rob van Holstein. So we correct for the instrumental polarization, and we are left with the real stellar polarization from the inner beam. So in this sense, we can already now detect, but not well characterized, compact disks. As for faint disks, we can go deeper. We can go a little bit deeper in our observation, but I don't expect to see much more than that. If a disk is faint at our wavelengths, it will keep being faint. Maybe if we go to LNM, because the extinction from the inner disk is lower, then maybe we could see a little bit more. But then the resolution is worse, so I don't know whether the game is really worth it.
Thanks a lot.
Okay, we just have a short amount of time, so let's go over here.
Hi, Artem Agishin from University of California, Santa Cruz. Also a question about your prospect. So you said, you mentioned smaller disks for PP8. I was wondering if similar methods could be used to unveil the characteristics of circumplanetary disks, and if we will have to wait PP100 for that.
Another good question. I don't know myself. At the moment, what we have is already something. I mean, having PDS-70B is already something. We don't know exactly what we see already in this example here. This is a very massive disk for sure. We know there is something. We know there is something based on the fact that the spectrum is very red, based on the fact that we don't see molecules from their atmosphere, based on the fact that the hydrogen line ratio is actually such that the extinction is high. Therefore, there must be something surrounding this planet. In some sense, I'm not even sure we're actually seeing the photosphere of this protoplanet. However, we go there without mine, we don't detect a circumplanetary disk. So even only in this case, where we have a massive planet well embedded, well within the cavity, we don't quite understand yet. So maybe we should try to understand this and then try to extend to the future. Not sure whether much before Protoplanet and Planet 8 we will have a good understanding of circumplanetary disk. Maybe I'm a little pessimistic, but I'd be happy to start having it by, let's say, Protostar and Planet 8-9, maybe.
Okay, last word and super quick question, super quick answer.
Super quick question, just related to the point that Inga made. Do you see any correlation with the accretion rate onto the central star of the morphology?
No, I never found anything.
Okay.
It's the only property that doesn't scale with brightness.
Okay.
Nothing else.
Okay, I think, do we have time for more, or is that it? All right, very, very quickly then, over there.
Olja Panic, University of Leeds. I'm going to be provocative and suggest maybe regarding the paucity of protoplanets, are we perhaps looking at the wrong place by looking at her big disks, and because of possible sequential giant planet formation, maybe the successful planet-forming disks have already dissipated?
Yeah, it's possible.
Are you aware of efforts in that direction to maybe explore, try to detect them where disks have dissipated?
So, sorry, I'm not sure I understand your question. So your direction to take would be to observe more debris disk or what?
Yeah, very young debris disks.
Yeah, that would be easier to actually detect this. We have a number of planets detected that goes along with debris disk. I'm not sure they are actually helpful to be able to characterize the planet formation itself, because there I assume that the planet is already formed. So for me, the most interesting moment would be this, the moment where really planets form. Even maybe they are not formed yet. We see a structure that somehow resembles an accumulation of material from which planets will form. Somehow I believe that this is the most interesting age.
I was referring to the same age, so young age, yeah.
Young age, but with disks already dissipated. Okay. Yeah, possibly. In a sense, no, we believe that these protoplanetary disks are the exceptional that can live longer, maybe around the big star, because just because we have pressure bump induced possibly by very massive planets. So somehow those disks where the disk is dissipated earlier, it's just because maybe we don't have a massive planet that can retain the dust there for a long time.
And it might be addressed tomorrow also. I don't know if they're looking at young stars, but anyway. Okay, so I think that's it. So let's thank both speakers.